up until now, we have thought of the force of gravity as the force that pulls us down to the earth, right? We've dealt with situations where you throw something upward and gravity pulls it down, or situations where a wrecking ball is hanging from a wire and you've got to balance the force of gravity and the force of tension, right? But gravity is more than that. And Newton discovered that. It turns out that gravity is the force that attracts all masses toward each other. And so universal gravitation is needed to describe more situations involving gravity than just the situations where you've got something being pulled to the center of the Earth. In fact, you've got the Earth revolving around the sun because of gravity, and Jupiter revolving around the sun because of gravity, and all sorts of stuff happening in space because of gravity. So we need a more universal law to deal with the action of gravity. And so Newton proposed the following: force of gravity equals G m1 m2 over r squared, right? It looks more complicated than what we've been using before. So we've been using Fg equals mg, right? And this little g over here is the acceleration of gravity, right, due to the Earth. You can also think of it as the strength of Earth's gravitational field at whatever point you're at, right? So I'm standing on the surface of the Earth right now, and so the acceleration of gravity, or the strength of the Earth's gravitational field, where I am, will be one value, but if I go to the top of Mount Everest, it'll be a little bit different. If I go to the moon, I'm still going to be pulled on by the Earth's gravity, but it'll be less because Earth's gravitational field decreases in strength as you get farther and farther away from the center of the Earth. And so that idea that the gravitational field strength is going to decrease over distance is reflected in this universal gravitation formula as well. This r value over here, we can think of it as radius, because that's often how it's going to be used. But really, we're talking about the distance from the center of one object to the center of the other object. So often it's radius because you've got one object revolving around the other. If we're talking about the force of gravity between the moon and the Earth, then we want that orbital radius of the moon between the moon and the Earth. If we're talking about the force of gravity between the Earth and the sun, we want that orbital radius of the Earth as well. And so radius makes sense, but only when you're talking about one thing orbiting another. So we could talk about radius or the center to center distance. Center to center distance. Okay, and that's going to be measured in meters. These two m's up here are the two masses that we're talking about. So again, if we're talking about, let's say, the Earth and the moon, m1 would be the mass of the Earth and m2 would be the mass of the moon, though it really doesn't matter which is which, right? You're just multiplying them together anyway. You would sometimes see this written differently as well. So sometimes you might see Fg equals G times big M times little m over r squared. And this is just another way of showing we're talking about two different masses. Okay. The last part of this thing that we need to understand is this G value. Okay, this G value over here is called the universal gravitational constant, and it's got a value of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, as you see just below there. So that value, you can think of it as the relative strength of gravitation as a force, compared to the other four fundamental forces that are out there. So the other fundamental forces would be the nuclear strong force, the nuclear weak force, and electromagnetism. And they all have a different relative strength compared to each other. And so in this case, that universal constant there, big G, is telling us how strong gravitation is compared to the other constants. It helps actually get the correct value for the force of gravity that's being exerted between two masses. The units of that constant are really not important to even think about at all. Those units for constants generally just help the units in the formula actually work out to the right thing on the other side. So we have mass and mass, or kilograms and kilograms. So we'll have kilograms squared on the top and meters squared on the bottom. But what we want to come out with is newtons on the other side, right? And so in order for the units to work out, we need Newton meters squared per kilogram squared as our unit for G. Again, not important. Really, you don't need to think about that. So let's see if we can use this in a couple contexts. What is the force of gravity between two people with masses of 65 kilograms and 70 kilograms if they are 1.5 meters apart? Now, whether this is from the center of one to the center of the other, or the surface of one to the surface of the other, is not actually going to make a difference, but let's just assume that that 1.5 meters is the center-to-center distance between these two people. So then we would use Fg equals G m1 m2 over r squared. This is a vector, but gravity is always just going to be attracting things to each other. And since we don't have a real directional context in this question, we'll just say attracting at the end. So we're calculating the force of gravity, and that's 6.67 times 10 to the negative 11. I'm not going to bother putting the units in there, times 65 kilograms times 70 kilograms divided by, and the distance between them is 1.5 meters, and we're going to square that. So it turns out that the force of gravity between these two people is a whopping 1.35 times 10 to the negative 7 newtons. And so, although you are attracted to the person next to you, I mean, unless you're watching this by yourself, you're attracted to them just a very, very tiny amount, right? You don't actually feel a pull to the other person because your masses are not nearly big enough to make a dent in that force. So let's talk about something a bit bigger, the force of gravity between Pluto and the Sun. Obviously much larger than people, so we'll see what happens if we have planets in here instead of people. F equals G m1 m2 over r squared. So we're going to calculate the force of gravity, and this is just going to be attracting again. Oh, I should put in the previous one, this is attracting or toward each other. And it's going to be the same thing between Pluto and the Sun. G is 6.67 times 10 to the negative 11. M1, we're going to say is the Sun, and so you can look up the Sun's mass on your formula sheet, and it's 1.99 times 10 to the 30 kilograms. And you can also look up Pluto's mass, which is 1.3 times 10 to the 22 kilograms. Great. And then this R value is the center-to-center distance between the Sun and Pluto. And we have another name for that. It's called the orbital radius of Pluto. So you can also look up the orbital radius for Pluto on your formula sheet. It's called mean orbital radius, and it's 5.91 times 10 to the 12. 5.91 times 10 to the 12 meters. And sometimes this happens when you're writing down so much scientific notation, so many different exponents. Sometimes people just forget this squared over here in the end. Really, really common mistake. Try your best not to. And so when we calculate this, the total force of gravity between the Sun and Pluto, we get 4.94 times 10 to the 16 newtons. So although they are very, very far apart, much farther than 1.5 meters, of course, because of how massive they are, the force of gravity between them is very much larger than between two people. And again, we can say toward each other or attracting, that's fine. Now, there are a couple other applications for universal gravitation that are very helpful, actually. So we can use that universal gravitation formula to calculate the acceleration of gravity near the surface of a planet. or really any distance from the surface of a planet if we want to. So let's take a look down here. Universal gravitation is always true wherever you go. So as long as you have the two masses and the strength of gravity, that's 6.67 times 10 to the negative 11 number, and the distance between those two masses, you'll always be able to calculate the force of gravity between them. But that doesn't mean that F equals mg is not true, right? Sometimes we have a partial picture that we then generalize or fill into more circumstances, and that's what's happening here. So F equals mg is still absolutely true when you know the acceleration of gravity wherever you are. And because on the surface of Earth, it's generally 9.8 and pretty close to that in all places, then we can still use F equals mg to describe what's happening with gravity on the surface of the Earth. Or if you happen to know the acceleration of gravity on some other planet, like on the moon, it's 1.6 meters per second squared, then you can still absolutely use this in those places. And so that means when we're near the surface of the Earth, or at least when we know, when we're near the surface of the Earth, then we can say that mg and gm1 m2 over r squared are equal to each other. That's what's being said right over here. Okay, so as long as the object is near Earth's surface, relatively near Earth's surface, then these two things are equal to each other. And so look what happens. M1 would be the mass of the object that we're talking about. Like we can assign whatever we want to those two m's, right? So sometimes it's helpful to go like this and use the big M little m notation. So then we would say Fg equals big M little or G big M little m over r squared. And then we would also say that the force of gravity experienced by an object is little m g, right? So the little m is the mass of the object. And in this case, we're just assigning that to m1. Pick one, it doesn't actually matter, but either way, the object is both of these m's, and so if we cancel both of those out, as we can do in that formula, you end up with a formula for the acceleration of gravity some distance away from an object. So let's say that m2 over here is the Earth, and if you wanted to know the acceleration of gravity some distance from the Earth, 100 kilometers from the Earth, then you could figure out what the acceleration of gravity was at that spot. Okay, if you already know the acceleration due to gravity, let's fix this a little bit, known. If you already know the acceleration of gravity on a planet, let's say, you can figure out the mass of the planet using the same system. Okay, you would then end up with this formula over here. Now, this is less useful, quite honestly. We're not actually going to do anything with that ourselves, but knowing the acceleration of gravity some distance from an object or planet, that is an actually useful thing to do. Now, the last part that we're going to talk about is how we would use universal gravitation with satellite orbits. Okay, so we send satellites into orbits, and when I say we, I mean humanity, not me in particular. We send satellites into orbit for all sorts of reasons. GPS satellites, communication satellites. There's a lot of satellites orbiting the Earth right now. And they all have different jobs. And in order to do the jobs they're designed for, they need to be a certain distance from the Earth. Okay, they need to be orbiting a certain distance. Otherwise, they will not operate correctly, right? So if you're trying to take pictures of the North Pole over and over again to track glacier recession, let's say, then you really need your satellite to be the correct distance in order to orbit over that spot over and over again, right? So we can calculate exactly what speed a satellite would need in order to be the correct distance from the Earth using the same universal gravitation formula. So we're going to combine a couple things here. We know that centripetal force, circular motion, remember, is mv squared over r. And in the case of a satellite orbiting, let's say the Earth, just for example, a satellite orbiting the Earth, the centripetal force that's keeping that satellite orbiting would be the force of gravity, right? And so then the second line over here, all we're doing is replacing Fc, because remember Fc is just F net for things going around in a circle, and then we make it more specific by saying what are the centripetal forces. Let's put those inside Fc. And in the case of a satellite orbiting the Earth, then Fg, or the force of gravity, would be the centripetal force. Okay, so now we've got the force of gravity is mv squared over r. Replace the force of gravity with the universal gravitation formula, and then we can make a couple alterations to it. Remember that m1 is the mass of the object. Okay, it says that in the note right over here. m1 is the mass of the object. We've just assigned it that way. We could make it m2. It's just then this would be m2 v squared instead. Okay, so it's just we've defined m1 as the mass of the object and m2 as the mass of the planet, Earth in this case. So now m1 occurs on both sides, and so we can remove that. There's also an r in the same position on both sides, and so we can get rid of one of the r's on the left and the r on the right, which leaves us with this final line over here. V squared is gm2 over r. So if I wanted to calculate the speed of a satellite orbiting the Earth at a certain distance from the Earth, I would need the Earth's mass and the universal gravitation constant, 6.67 times 10 to the negative 11, and that would allow me to calculate the speed of that satellite. Of course, this is speed squared, and so I would need to square root it at the end, but very, very useful formula. If I'm launching a satellite into space and needed to do a certain job, I need to make sure it's going the right speed to orbit at the right distance from the Earth. Let's try one last example about satellites here. A satellite is in geosynchronous orbit around the Earth at an altitude of 35,786 kilometers. At what speed is it moving? Okay, so we're looking for the speed of a satellite in orbit around the Earth. One of the tougher parts about this whole space exploration section is that there are a lot of different formulas that look very similar, that have a lot of similar pieces to them. And so it's important that you identify what it is that you're looking for and what sort of situation this is. So this is asking us for what speed is it moving. So that's v. We're looking for what speed is it moving, and hopefully that narrows down what tools you have available to you, what formulas you actually should be working with here. Okay, so we should keep in mind what the satellite is orbiting. This is orbiting the Earth at this point. If it's something going around the sun, then it's possible that we should really be using one of our sun formulas instead, like the k equals r cubed over t squared. But in this case, this is an Earth satellite, and so we're trying to figure out how fast is it moving. That points us to the last formula that we just learned. So it tells us that it's in geosynchronous orbit. That doesn't really give me any information I can use in the formula, in the problem solving itself. But it turns out that all satellites orbit, if they're geosynchronous, they orbit at 35,786 kilometers above the surface of the Earth. And that brings up an important point, that distance is the height above the surface of the Earth. So when we use this, v squared equals gm m2. I mean, I'm not going to use m2 in this case just because there's no purpose in putting a 2 on it. It's not the second mass. It's really nothing like that. And so often you'll see instead g big M over r, just to tell you that the mass we're using here is not the mass of the object, not the mass of the satellite, it's the mass of the thing being orbited. So the Earth, in this case, we want the Earth's mass in that spot. So you could, if you wanted to, put ME here to tell you that we're talking about the mass of the Earth, but it's just big M. This R value, though, is the distance from the center of the Earth to where the satellite is. And so there's a lot of temptation to just shove in the altitude into that spot, but we actually need more than that. We need the distance from the center of the Earth to where the satellite is above the Earth. So we're going to need to add together the radius of the Earth plus the altitude of the satellite. Okay, so that's the tricky part of this thing. Everything else is fairly straightforward using this formula if you've selected the right formula. So here we go. V squared equals 6.67 times 10 to the negative 11 times the mass of the Earth, which I looked this up, is 5.97 times 10 to the 24. These numbers are all on your formula sheet, right? Just look in the back in that table of planetary information. And then this R value, like I just said, needs to be the distance from the center of the Earth to where the satellite is. And so I'm going to put the Earth's radius here first, which is 6.37 times 10 to the 6 meters, plus then the altitude above the surface of the Earth, which is 35,786 kilometers, but I need meters, right? So another little detail that I have to keep in mind here that can trip people up. So 35,786 is 000. This is meters. This is meters. Now you'll notice that very often I put the units in when I'm doing problem solving like this. I insert the units within the calculation itself. You do not have to do that, but it can help you make sure that you're doing this right all the time when there are units that need to be converted. So if I write down 35786 kilometers into that spot, hopefully that tells my brain, oh wait, no, kilometers is wrong. I need to convert this to meters. So there it is, meters. Now, when you do this calculation, and hopefully you do it on your calculator correctly, personally, I would put brackets around this bottom part because there's adding in here, and I don't want it to go 6.67 times 10 to the negative 11 times the mass of the Earth divided by this first thing equals, and then add on the altitude above the surface. I want it to do all of this at once. So we do that, and then we need to make sure that we square root that answer, and we should get 3073.4. I mean, not very important, but especially because the number of sig figs, well, I guess there's 5 sig figs, 30.3.4 meters per second. And that's the speed of this satellite orbiting the Earth.